let's talk about how we measure climate and various parts of climate. Because this is the only way that we know what climate is now and how climate is changing. We need some way of measuring climate, both today and in the past, with what we might call proxy records. So we can talk about direct measurement that only works for time periods that humans have had accurate thermometers. So like 1850 to today or so. Looking back in the past, we can use all sorts of things to get a proxy record of climate that we have to put a lot of work into figuring out how different variables reflect the climate. But one of the ones that people think about a lot is tree rings. And that has some familiarity with folks, that when a tree is doing well, it puts on a lot of mass on its outside and grows thicker rings. When a tree is not doing so well, it grows thinner rings. And we can correlate that with climate, especially if we look at a lot of trees over a lot of different areas. Other things that we can use as a proxy record of what climate was is the pollen in an area. If we have pollen stored in, say, lake sediments, that will tell us about what the plants were around. And if we see a shift in the plants that are present, that can reflect climate. Ice cores end up being a really good repository for these proxy records because they record a couple of different things about climate, as do carbonate sediments. And then there are also some records of solar influence that we have used to look at the important hypothesis, which is, well, if climate is changing and sun is the biggest control on climate, is it just the sun changing that's influencing climate today? And we'll look at that. So here are some examples of direct measurement, either with land-based thermometers or sea-based thermometers, or even sort of thermometry by satellite measurements. These all agree that we've had about 1 Celsius of warming since 1850. And so we've changed from about here to about here, give or take, a little bit. There's certainly some wiggles around there, but the general trend has been about 1 Celsius of warming since 1850, much of it happening in the past 100 years or so. Because these are direct measurements, and because we haven't had thermometers, certainly back 1,000 years ago, these direct measurements are only available for about 150 years. You may have heard at some point, if you were in this discussion and into climate science, some folks saying that the satellite records and the thermometry records don't agree, and that's a problem for climate science. But a lot of those concerns have recently been put to rest. If you want to read some papers about it, here are a few to get started. Tree rings are a proxy record. We can also call them dendroclimatology, right? We're reading trees to tell us about climate. It's because trees lay down thicker rings in warm, moist summers, or at least they tend to, especially if they're in climates that match those trees' preferred climates. The nice thing about these tree rings is that they have annular resolution, right? Yearly resolution. That one of these rings is laid down every year. So that by looking at the years when you have thick rings, you can find rainy seasons, or you can have dry seasons when there are very thin rings. You can also have other things recorded like scars from forest fires that can tell you about other local conditions going on. And if you stack these trees up, some dead trees from today, some dead trees, from 200 years ago, from 400 years ago, on and on and on, you could actually stack these tree rings up and look at how they correlate with one another, and you get a long enough record, you can go back thousands of years into the past. That being said, multiple factors are affecting these, right? It's not just temperature or just precipitation. All these factors are feeding into these, so the records can be fairly noisy. And you need a large combined record over a large area, all sorts of different types of trees, to get a really good tree ring proxy record, which is what we do. It takes a lot of work, but it's what we do. Pollen records, aka palynology, are ways of using the pollen present in sediments to reflect the ecology and the climate at a site over a specific time. You can actually go millions of years into the past if these things are well preserved and if analogous species still exist. And just like dendrochronology, like the tree ring that we were looking at, multiple factors do affect these, but these have the benefit of sort of aggregating across species. And so like in this particular environment, it shifted from a spruce-dominated environment, right, like sort of boreal taiga, pine tree forest 14,000 years ago, to an ash, elm, and oak-dominated forest shortly thereafter for several thousand years. And then over the past few thousand years at this site, the forest has mostly given way to a more grassland ecology. And put enough of these together, and you get some understanding of how the climate has changed over time, because each of these trees we know a lot about, and we know about their climate preferences. Ice core data is some of our best records of the last million years or so of climate change, and some of these can go back as far as a few million years. They work for two reasons. One, as snow rains down, that will later turn into this ice cap ice, which is where we extract the ice cores from, they trap bubbles of atmospheric gas, which we can use to tell the composition of the atmosphere over time. So carbon dioxide, has varied in this particular record from nearly 180 parts per million up to about 300 parts per million in the atmosphere. And today, we've shot up way past 400 parts per million. That's by human impact, and we'll talk about that. But the past record of how much carbon dioxide was in the atmosphere, or how much methane, or how much of other gases is actually recorded in those ice core bubbles, which is pretty nice. Another thing that we can read from these ice cores, we can actually read the temperature of them because of the isotopes in the ice. Let's not talk too much about just why, except to say that heavy isotopes, oxygen 18 instead of oxygen 16 in particular, those evaporate more and enter ice more when it's warmer. So that when it's warmer, we'll have more heavy isotopes, and when it's colder, we'll have more light isotopes. And so that's how we actually get temperature records from this ice core data. We read enough of the oxygen isotopes in the water stored in the ice over time to get that sense. So that's a pretty big benefit, that we can read temperature directly from these. And they don't have as many of the caveats as, say, the tree ring record or the pollen records do, but they only record temperature of the polar regions. So that's kind of a shame. Now, that can correlate with global temperatures, but it doesn't have to be perfectly reflective of those. So other records are necessary too. Another good long record is carbonate sediments. So, right, we've talked about limestone forming, and we can read limestone in the same way. They store more heavy isotopes when it's colder, in this case. And with some carbonate sediments that are generated by things like corals, they actually lay down annual rings, much like tree rings. So as long as we can, go back with corals, maybe a couple of thousand years, we can actually get an annual resolution of climate reading those. And we can match these up to our, past 150 years of instrumental records too. And we find there's a pretty good agreement with those. Some of these, like shells of plankton that fall in deep sea sediments, can last millions of years. So these carbonate sediment records can extend back a really long way. And an added benefit is that these sediments don't have to just be in the poles, right? They can be in tropical areas, or they can be in open oceans and other places. So they can tell you the temperature of all sorts of places around Earth. I'll end with these records just mentioning that there are some records of solar activity. It's harder to measure than temperature or than gases in the atmosphere because the only way that we've figured out how to get at those solar activity levels are certain unstable isotopes that are produced in the upper atmosphere by solar radiation over time. Weird stuff. The fidelity of that record, the precision of that record is lower. It's less precise than records of, say, temperature. But we can get some idea of how variable cosmic rays have been over, the past 1,000 years or so. It just doesn't have great resolution. As far as we can tell, though, that solar activity doesn't seem to be what's driving the changes in the past 150 years.